T is the target language, and basically language I in which the compiler is written. This is the basic structure, and this is the corresponding T diagram. This is the source diagram. This is the target. This is the source language. S is the source language. This is the target language, and this is the language by which in which the compiler is written. And this representation is known as the T diagram. Now, T diagram this T diagram is symbolized in this thing CST I. That means C. This is S is the source language, T is the target language, and I the by which the language is compiler is written. By using this concept, what we can do, we can create a compiler that may run. Just correct this thing that may run on one machine and produce target code for some other machines, and this compiler is known as the cross compiler. We just write these things. This is not properly visible. Using this concept, we can create a compiler that may run on one machine and produce target code for some other machines, and such compiler is known as the cross compiler. Okay. Now just see, this is the first concept or development of the first compiler, in which knowing only the machine code, M is the machine, using this machine code, write a compiler for the language S. That means source is the S is the source language, your target code is M, and the compiler itself written in the M language also. And this is basically its corresponding T diagram. That is what we have done. We have written a compiler in M language, which was the previously known code M, to create a compiler for the language S. And this concept has been used in the C language. I have given you the answer that thinks that how C compiler compiles itself. Now, you just see next one. Since we have created a language S, and this can be used to write other compilers. Once we have done for a compiler for the language S, this language S can be used to write a compiler for creating a new language. That means right now your source language is L, and N is your target code, and the compiler is written in the source S language. That is, source is L, target language is N, and the compiler is written in S language, because we are generating the compilation or compiler of the S language itself here. And its corresponding T diagram is like this thing, C, L, and S. Now, we just see next one. Now, the language L produces a code for N, we have seen. Now, what will happen if L is run on the previous machine? L is run on the previous machine M, in which a language S has been created using the M. That is CSMM, this one, CSMM. Now, this can be seen as a new compiler. You just see C, L, and M, because why? We are coupling these things, combining these things, that is C, L, and S. Here in this T diagram, L is your source language, N is your target language, and S by which the compiler is written, which run on these things, because compiler is written in the S language. That is, we are getting the compiler of S language also. That is, S is running and producing the target code M, and compiler S is working on the machine M also. That means S is written in the M language, and that is why finally what we are getting? We are getting LNM. LMN. What is that? That means finally we are getting that L is the source language, N is the target language, and the compiler is running on the machine M. And this technique is known as the compiling a compiler. This technique is known as the compiling a compiler, or it is also known as the cross compiler technique. Is it okay? Are you understanding these things? Okay. Scanning is not done properly. Okay, I'll send you this. Now, you just see this formula, actually this T diagram, LNS, SMM, LNM, this can be represented using these things. That is, CLNS runs through CMMM and produce CLNM. Now the question arises, why we have used CLNS to create a CLNM, M being the known previously. That is why we want to create a compiler running on previous machine M, and its importance will give clear that when you are using a series of compiler to create a new one with a little effort, as one compiler may be compatible to one machine but not other, and that is why we are using this concept, and that is known as the compiling a compiler or cross compiler. This compiler is basically, technique is known as the compiling a compiler, or this compiler is known as the cross compiler. Cross compiler. Again, I'm repeating these things. And this compiling a compiler, this process is also known as the bootstrapping process. Bootstrapping process. You just see, just try to understand this problem. Example 1.8. SAA and LSA, and what are we getting? Like the previous example, we are getting from CLAS to CLAA. Is the thing. Same way, just previous example in this way. And see the another things, how the cross compilers are created using the bootstrapping. You just see CLBL. Now intermediate is CLAA, and we are getting CLBA. Same way. Concept is same everywhere. And next example, you just see these things. I think this is clear.
Yes, sir.
Yes, sir.
Now, just see. Just try to remember the bootstrapping process again. I'm just telling you the process of bootstrapping. What I have seen, just we will see it again. Bootstrapping means compiling a compiler. The basic idea in bootstrapping is to use compilers to compile themselves or other compilers. We do, however, need a solid foundation in the form of machine to run in the compilers on. That is, write a compiler in the source language, that is we have seen. There is no compiler for the source language yet. Now, porting to a new host machine. First step in the bootstrap is like these things. This one, AHA, AHH, now AHH. Same way. That is quick and dirty compiler. That means that right now it is written in the H, that means machine code, and that is why it is known as the DATI compiler, because language, the code of the compiler may not be understandable. That is, quick and dirty compiler written in the machine language H, compiler written in its own language A, result in running but inefficient compiler. Now, running but inefficient compiler, this is the bootstrapping. Second step, a compiler written on its own language A and results in the final version of the compiler. This is the things. First one, what we are writing the compiler in this way, AAH, AHH, and finally we are getting AHH. These are the things. That is, first one, A is your source language, and that maybe you just consider this source language and A is your machine language also. And now you are generating a new machine, new compiler with the help of this concept, bootstrapping concept. That is, we are getting, instead of machine language, you are right now in a position to write the compiler from AAH to AHH. These are things. And what about the porting? Porting is like these things. Porting is the process of adapting the software so that an executable program can be created for a computing environment that is different from one for which it was originally designed. Again, I'm repeating these things. Porting, mobile porting, same thing. Porting is the process of adapting software so that an executable program can be created for a computing environment that is different from other or different from one for which it was originally designed. That is for different CPU, different operating system, or different library functions like these things. The term also used when the software or hardware is changed to make them usable in different environment, and that is known as the portable one. That is, software is portable when the cost of porting it to a new platform is less than the cost of writing it from the scratch. And lower the cost of porting the software relative its implementation cost, more portable it is to be. You just see. First one is the original compiler. Compiler source code retargeted to K. That is, you just see, A is written. A is the source language, K is the target language, and the compiler itself written in the A language A. Now, with the help of this machine, we are converting these things AHH. Now, what are we generating? AHK. That means source language is A, target language is K, and compiler is written in the H language. Now, with the help of this concept, AKH, what are we getting? Now, AKA, initial one. Now, instead of using this concept, we are using AKA, now AKH. We are getting AKK. That means, that is what is that? Compiler source code retargeted to K, and that is done there. Yeah, actually. That is, we are getting original compiler source code retargeted to K, this one, and result in the cross compiler. Now the cross compiler we have got this one, cross compiler source code retargeted to K, and result in the retargeted compiler. Just see. And this technique is known as the porting. This is most important part of the compiling a compiler or generating the cross compiler. Is it okay?
Yes, sir.
Yes, sir.
Isa,
Yes, sir.
you just tell everybody, try to join before the class or within 10 minutes from the starting of the class.
Okay, sir.
Okay, another thing you just write, difference between native compiler and cross compiler. Just write native compiler versus cross compiler. Basically, what do we mean by the compiler? By the term compiler, we mean native compiler. Okay, I'm just telling you what is native compiler. Native compiler are the compilers that generates code for the same platform on which it runs. Again, I'm repeating these things. Native compilers are the compilers that generates codes for the same platform on which it runs. It converts high-level language into the computer's native language. For example, Turbo C or GCC, all are the example of the native compiler. Are you understanding what is native compiler? Native compiler are the compilers that generates code for the same platform on which it runs. That is, it converts the high-level language into the computer's native language. An example of the native compiler are the your Turbo C compiler, or in the Linux environment, the GCC compiler is the native compiler. This is faster. Next one is the cross compiler. What is that? We have already seen. Cross compiler is a compiler that generates executable code for a platform other than one on which the compiler is running. The cross compiler is a compiler that generates executable code for a platform other than one on which the compiler is running. For example, a compiler running on Linux environment maybe running on Linux environment is building a program that may run in the Arduino environment. This is basically known as the cross compiler. Again, I'm repeating these things. A cross compiler is a compiler that generates executable code for a platform other than one on which the compiler is running. For example, compiler running on a Linux environment and building a program which may run in the Arduino One, separate Arduino One. Okay, this is the difference between cross compiler and the native compiler as well as the cross compiler. Now,
Sir, can you give me the one example of cross compiler?
I have told you again, that is compiler running on a, just see, a compiler running on a Linux environment and generating some program which may be applicable in the Arduino environment. Then you can say this is the cross compiler. So writing the compiler in a particular machine, and the compiler may be used for that or another environment or another machine. And this is basically known as cross compiler. Okay.
So native compiler depends on the operating system.
Anikta the body. Compiler depends some portion of operating system. Target code generation, code optimization, in that case, and just architecture. That means it has been allowed to register for these things for generating the target code. In that case, operating system has also some role to play. In the latter half of the compiler.
Okay, sir.
Now, we will see next one is the lexical analyzer. First one we will see. What is the role of the lexical analyzer? Can anybody tell me? Yeah. Convert the source language into the corresponding tokens or lexemes, whatever may be the name of these things. Okay, you just see here, lexical analyzer source program is to convert it in the tokens, and token is passed to the parser or the syntax analyzer, and parser may ask for the next token like these things, and both of them takes help of the symbol table. That is, lexical analyzer puts the token into the symbol table, and parser may take the tokens from the symbol table itself, or sometimes lexical may directly send the tokens to the parser, but parser may take help of the symbol table for matching the, in case of mismatch of the tokens, it also consult the symbol tables. Okay. You better write something about the role of the lexical analyzer, because this is a quite common question. What is the role of the lexical analyzer? Lexical analyzer acts as an interface between the input source program that to be compiled and for the later stages of the compiler. Again, I am repeating these things. Lexical analyzer acts as an interface between the input source program that needs to be compiled and for the use of the latter half of the or latter stages of the compiler. Input program can be considered as the sequence of characters. Input program can be considered as the sequence of characters. Lexical analyzer converts this character stream into a stream of valid words of the language, which is known as the tokens. Again, I'm repeating, lexical analyzer converts this character stream into a stream of valid words of language known as the tokens. And the parser looks into a sequence of tokens and identifies the language constructs occurring the input program. That is, you can say the parser and the lexical analyzer work hand in hand. What is the meaning of these things? That whenever parser needs for the tokens to be proceed, it requires the lexical analyzer. You just see in the diagram it is given. And lexical analyzer in turn scans the remaining input stream and returns the next token occurring there. Apart from these things, lexical analyzer also participates in creation and maintenance of the symbol table, which may be used by the other phases of the compiler. That means lexical analyzer directly sends the token to the parsers. Parser may ask for the next token. It will also send these things. But sometimes in case there is some problem or like these things, parser, that means sequence mismatch or like these things, parser may consult the symbol table, which will be created and maintained by the lexical analyzer itself. And basically, what the lexical analyzer puts, just remember this: lexical analyzer puts in the symbol table the symbol and its location. That means where it has been stored, like these things. In the memory, it has put these things. And also some other fields of the lexical analyzer, that is size, type, etc., are generally put by the, that is filled up by the parser itself. Are you getting me? How like symbol table is generating?
Yes, sir.
That means when you are just, what is your source program? Source program is your, you just try to remember the first day what I have shown you. That is how the basically a sentence can be converted into the machine code that I have shown you. Basically, this sentence basically maybe consists of several symbols. For example, you just see ID assigns to, if we have told you ID assigns to ID, ID1 assigns to ID2 plus ID3. In that case, symbols are the ID1, ID2, ID3. These are the symbols. Basically, these are the variables. Basically, everything is simple. Assigns to and plus maybe another type of tokens. That is ID1, ID2, and ID3 are the one type of token, part of the variables, and assignments and plus maybe the another type of tokens. Another type of tokens that is basically used in the arithmetic operations, arithmetic symbols. Basically, all are the symbols and all are the tokens. Now, what the lexical analyzer do? Lexical analyzer will put that all the symbols, that is all the tokens, into the symbol table, as well as its location where it has been stored in the memory. Its location also be stored there. But what the, after that, what the parser will do? Parser will fill the remaining portion of that symbols, that is the type of the symbols or maybe the size of the symbols, like these things. If the variable is of integer type or the variable is a float type, like these things, it will put the type and size of the, that means type means it is a, this symbol or this token is of type variable, this token is of type what should I say, this token is of type arithmetic, like these things, arithmetic symbol, like these things, as well as its size will be put by the parser. That means symbol table, maintaining and creation of the symbol table basically done by the lexical analyzer, and some part has been, symbol table has been filled up by the parser itself. That is, again I am repeating these things. That is, lexical analyzer is mostly used for filling up the part of the, that is mostly used for creating and maintaining of the symbol tables, and some of the other fields of the symbol table, that is type, size, etc., are generated by the, or simply filled up by the parser itself. And for later occurrence of the symbol table is scratched to extract the relevant information about it. And lexical analyzer is also responsible for removing the cosmetics from the program, like extra the white spaces, comments, etc. This is basically also done by the lexical analyzer. That means cosmetics, that means additional one. That is extra white spaces, comments, etc. Lexical analyzer is responsible for removing these things also. Got it? Yes. And why we have separated the lexical and the parsing? Because we have seen the lexical, although lexical and the parser are working hand to hand, but for the simplicity of designing, I have just separated lexical analyzer as one phase, parsing is another phase. For simplicity design, improving the compiler efficiency and enhancing the compiler portability. For that, we have separated the lexical analysis and the parsing. Now, let us see what is tokens, pattern, and lexems. This terminology is very important. Just a minute. A token is a pair of token name and an optional token value. That is, if the token is of type identifier, identifier may have some values, and in that case, token may have values. But token is of type arithmetic symbols. In that case, it will don't have any value. And what is a pattern? Pattern is a description of the form that the lexemes of a token may take. And what is a lexeme? A lexeme is a sequence of characters in the source program that matches the pattern for a token. That is, first one is the token. Token is a pair of token name and an optional token value. Pattern is the description of the form that the lexemes of a token may take. And lexeme is the sequence of characters in the source program that matches for the pattern of a token. Sequence of character is basically the lexeme one. And when it matches the pattern of a token, then it will be said as a token. Then it will be said as a token. Okay, for example, suppose a variable. Okay. Can you tell me how a variable can be defined in any programming language?
Data type, through data type.
I'm asking you how a variable has been defined. A1 is a variable or 1A is a variable?
A1 is a variable.
A1 is
Underscore A is a variable?
Yes, sir.
Hmm?
Yes, sir.
Underscore 9 is a variable?
Yes, sir.
No, sir.
no, sir.
Number variable.
Just tell me. Underscore followed by 9 is a variable or not?
Yes, sir.
9 underscore?
No.
sir.
No, sir.
Yes.
No, sir.
That is the things. You just see. Suppose we are writing a variable. That means we are writing a sequence of characters. A, B, C. Okay. ABC is a lexeme. Okay. As well as ABC is a token. Basically, it is matches with an identifier. Are you understanding? Just a minute.
No, sir.
You just see when we are writing this in this way. A, B, C. What is that? This is a sequence of characters. No doubt about these things. Okay. Now, this sequence of characters, this is a sequence of characters. This is known as the lexeme. First one. This is a sequence of character. For example, 9ABC or 9AB. This is also a sequence of characters. Okay, characters or just say, okay, this is a sequence of symbols or this is a sequence of, what should I say? Yeah, this is a, if we consider this is a sequence of letters and alphabets. Okay, this is a sequence of alphabets, this is a sequence of letters, but this is a sequence. This is a lexeme, this one is a lexeme, this one is also a lexeme. But can this be a ABC may be considered as an identifier, that is, it will generate a tokens. But can 9AB may be generated as the identifier?
No, sir.
No.
No, sir.
That is why it may be the lexeme, or it cannot be recognized as a token. Here, this is a lexeme, but this is not a token, 9AB, because this cannot be any form of the tokens. This cannot be any form of the tokens. Got it?
Yes, sir. Yes, sir.
Yes or no? Tell me clearly whether you are understanding the difference between lexeme and the tokens.
Yes, sir. Clear.
Yes, sir.
This is a lexeme. Lexeme is a sequence of characters. ABC is a lexeme, 9AB is also a lexeme. But ABC can be recognized as, for example, we're just doing int ABC. This is possible. AB. Second one is possible.
No, sir.
That is why
No, sir.
this one cannot be considered as the variables or the identifiers. That is why 9AB may be a sequence of characters, may be a lexeme, but this is not a token. That I want to say. Okay, so that you just understand the difference between lexeme and the token. Now, what is a pattern? Pattern basically you just see, that means pattern of a particular token is known as the, basically how the token has been generated. How the token has been generated, that is definition of, for example, what is a identifier? Actually, we know identifier is starting from a letter followed by a letter or a digit. Is it? Identifier, that is variable. Variable should started with a letter followed by a letter or a digit. Is it?
Yes.
Why I'm not getting the proper responses? Identifier, I'm telling that identifier, starting identifier means variables. It is started with a letter followed by a letter or digit. But this is basically the pattern. This is basically pattern. Letter followed by a letter and digit. This is basically pattern. That means three terminologies commonly associated to each other. That is token, lexeme, and pattern. Token, lexeme, and pattern. Okay, and it should be clear to you. It should be clear to you. Now, just a minute. Now just come to here. Now see. Okay, maybe like these things. If else comparisons, ID, number, literal, all are the tokens. Informal descriptions, if means I followed by if. Else. Comparisons, less than, greater than, less than equals to, greater than equals to, not equals to, like these things. Identifiers, as I've told you, letter followed by letter or digits. Number means any numeric constants, and literal anything but surrounded by the double quotes. And these are the simple lexemes for each of the type of the tokens. Each of the type of the token. Got it?
Yes.
Now, you just tell me in this printf which one is the token and what is the corresponding lexemes. Just tell me.
Token is the literal.
Hmm?
Token is the literal, and the lexeme is that thing inside double quote.
Yeah, whatever may be written in the double quote is the literal. Okay, no problem is there. That means total equals to %d plus n. This is literal also. That means anything surrounded by double quote. It is okay. Now followed by what are the tokens?
So the opening and the closing brackets, then the
Printf.
semicolon,
Printf is a token.
core printf.
Just start with the printf. Printf is a token. Is it token or not? Tell me. And which type
Yes, sir,
of
token.
it should be? Which type of token it should be?
Function name.
Keyword. Simple way, keyword. Total and score. This is also a token. What type of token it is? Hmm? What type of token it is?
Sir, is code an identifier?
Total and score is an identifier or variables. Identifiers or variables, whatever may be. Okay. Equals to percentage. Actually, %d is basically only used for the C language. Okay. This is not common. This is a special case. And /n may be in the terms of the new line, that is white space characters or like these things. That is additional space. And if you consider equals to maybe the, what is that? It is part of the arithmetic tokens, type of the arithmetic tokens. Okay, these are things. That means there are several tokens we have seen in this example. Now we just see here another example of the token, attributes for the tokens. E equals to MC square. M into C. First one is ID. There is pointer to the symbol table entry for E. Next one is the assignment operator. Name M is another ID. Now multiplication operator. C is another ID. Exponential operator. And next one is the number having the integer value 2. These are the various types of tokens here. we can see these things. Is this example clear? See these things clear properly?
Yes, sir.
Yes.
It's easy, not a difficult one. Now you just see lexical errors. What type of errors may be these things? As we have seen, there are different types of errors in the compiler, and each phase compiler may have to taken care of these type of errors. That is lexical errors, parser errors, semantic errors, errors related to the intermediate code generation, code optimization errors, as well as the target code generation errors. These are the various types of errors. Now, you just see, instead of if, we are writing while. This error, that is mismatch in the keyword, and this is the errors. But when you deals with the compiler, that means sometimes this one deassigns to basically, but this error may be identified by the lexical analyzer or may not be, because instead of if, phi may be phi. What is phi? Phi may be an identifier. These are things. Lexical analyzer may not be recognized this type of error, which will be handled by the next phase, that is the parser phase. But this type of error may be recognizable by the lexical analyzer itself. That is D assigns to 2 into R instead of it is written as 2R. And just see, that is why, as we know, variables cannot start with a digit, and that is why these errors can be recognized. If the compiler has been designed in such a way that variables should start with a digit, then 2R may be a variable also. That is, these type of errors are recognized when no pattern for the tokens matches a character sequence. Now, define types of error recovery. Define types of error recovery in the lexical analyzer. First one is we have seen, actually already we have seen the some error recovery strategies, that is types of the errors we have seen: lexical errors, syntactic errors, semantic errors, and the logical errors. Okay. Again, I am repeating these things. Can you tell me what type of errors may be handled by the lexical analysis? That what is the lexical errors? Or what should be the lexical errors? Just try to tell me. Because without error handling routines, you cannot even start off writing the compiler.
স্যার ইন্ট কে যদি ভুল লিখে ইন্টিজার না লিখে আইএন লিখে ওটা একটা লেক্সিক্যাল টাইপ অফ এরর।
Hmm. Just that is the
Certain, if we use opening bracket and don't close it, or we are commenting something and we don't close that comment,
yeah, that is the
then these
thing. But these errors is not the lexical errors. Lexical analysis cannot identify these things. That means starting with the parenthesis, opening parenthesis there, but no closing parenthesis there. That will be taken care of the parser when designing the corresponding parse tree. Okay. But yeah, this is also error, but this is not taken care by the lexical analyzer. First one, errors taken care by the lexical analyzer mostly due to the spelling mistakes and sometimes accidental insertion of the foreign characters which may not be supported there, like these things. This is the lexical analyzer. That means instead of what she says, that instead of int we have written in. Okay, ina. This is the spelling mistakes. Sometimes maybe just you have defined an identifier properly, but when you have used the identifier, you have not given the proper name. These are things. In that case, these are the errors taken care of by the lexical analyzers. Now, in case of the syntactic errors, that's what we were saying. That means grammatical mistakes like unbalanced parentheses in the arithmetic expressions, ill-formed constructs, etc. This is basically errors mostly in the programs, and parser or the syntax analyzer has been designed to take care of this type of errors. Now, semantic errors. Semantic errors, that is the errors due to some undefined variables. Errors due to some undefined variables. This is first one. Incompatible operands to an operator. Like these things. Incompatible operands to an operator. And these errors have been taken care by handled by the semantic analysis phase. And sometimes semantic errors may be are the logical errors. That means errors generated by the infinite loops, like these things. Basically, there is no such way to find. That is, sometimes you may face that your program is compiling properly, but it is not giving expected results. In that case, you need, what you have to do, you have to trace or debug your program so that you will be able to understand why this proper result is not coming. Now, this is the errors. And what are the error recovery strategies? What is the error recovery strategies? First one is the panic mode error recovery strategies. Okay, panic mode error recovery strategies. What is panic mode? Basically, in this case, the parser discards enough number of tokens. You just see, parser discard enough number of tokens to reach a decent state on the detection of an error. That is, successive characters are ignored until we reach a well-formed token. A set of tokens marking the end of language construct is defined to make a synchronization set. And the parser discards tokens till it comes to across a token for the synchronizing set. These are the things. For example, synchronizing tokens are the semicolon, choosing braces, in, etc. That is, which are basically meaningful for terminating the statements or the blocks. Okay, just a minute. That means what is done in the panic mode? That means successive characters are ignored until you reach to a well-formed tokens. That means parser discard enough number of tokens to reach to a decent state on the detection of errors. And we know basically a set of languages marking the end of, that is set of tokens marking the end of language construct is defined as the synchronizing set. And we will try to find out that synchronizing state in the panic mode error recovery. That means we go on discarding, we go on deleting something, the characters, until we reach some of the synchronization sets like semicolon, closing braces, in, etc., like these things. And this is basically known as the panic mode error recovery strategies. Got it? This is first one, panic mode. Next is the phrase level error recovery. Phrase level error recovery. What is that? Panic mode is one type of error recovery strategy. Next one is the phrase level. In the phrase level, parser makes some logical corrections on the remaining input on detection of an error, so that the resulting input stream gives a valid construct of the language. Again, I am repeating these things. Here in the panic mode, phrase level error recovery, the parser makes some logical corrections on the remaining input on detection of an error, so the resulting input stream gives a valid construct of the language. What are the examples? Examples of this category include replacing a comma by a semicolon, inserting something, a missing character, etc., etc. But sometimes inserting a new character may be problematic. That means it can generate more errors. It can generate more errors. That is, we have seen there are two types of error recovery strategy. We have already seen, that is panic mode error recovery. Another one is the phrase level error recovery. Third strategy may be the another technique, that is error production. Error production. This involves modifying the grammar of the language to include the error situations. In this case, what the compiler designer do, compiler designer must have a good idea about the possible types of errors so that he or she can modify the grammar appropriately. And this type of erroneous input program is valid for the new grammar augmented by the error productions. And the parser can always be proceed. That means grammatical mistakes is there. In that case, compiler designer may do the or done the necessary corrections. This is basically known as the error productions. That is, we have seen three approaches of the error recovery: panic mode, phrase level, and the error production. Is it clear? Or something you need to know these things? Okay, I'm sending this error handling page to you. Okay, you just go through these things. This is the little bit of tougher one. Isa,
Has it?
I have sent you the
হ্যাঁ স্যার আমি সেন্ড করে দিয়েছি
okay. Okay, next day I will discuss about the remaining portion of the input buffer. That is, this is input buffering. This is part of the lexical analysis, and you just try to go through. That means what you have gone through. Two things, that is DFA and FA, and some portion of the grammars. You just quickly go through what you have taught in the previous semesters. That is in the formal language automated classes. Got it?
Yes, sir.
Okay, that is. See you in the next class.
Okay. Thank you, sir.